Welcome back to the IB Maths Doctor channel. In this video we are covering the product rule, part of Unit 6, specifically section 6.2. And in the IB syllabus this is SL 5.6. We will just cover the product rule today. There is more to this part of the syllabus involving chain rule and quotient rule. Those will come in a future video. So let's dive straight into the product rule and what it is and what it can do for us here. So we're at the point where we know how to take the derivatives of lots of different kinds of functions, and now we're going to start looking at kind of combinations and mixtures of those functions using mathematical operations that are more advanced than just addition and subtraction. So we start with product. So we're talking about the product of two functions, which we will call u of x and v of x, and we are multiplying them together. And we're going to begin with a little investigation with essentially a factored polynomial and talking about how we might differentiate this product right here. So we know from the previous unit that we can actually remove this product by multiplying this out and turning it into a polynomial in standard form. So if we do that, we'll get f of x equals 2x cubed plus x squared plus 6x squared plus 3x. And we can simplify that by combining the two middle terms to 2x cubed plus 7x squared plus that 3x. Now this is just multiplying out. This is not actually calculus, but at this point we can apply our power rule to just take the derivative as we've done many times, giving us 6x squared plus 14x plus 3. So this is a problem that is carefully cooked up where we can actually work our way around having to take the derivative of a product by just turning it into a regular standard form polynomial. So the reason we're doing this is to try and answer this next question, which essentially says, is the derivative of a product just the derivative of the two components of the product? So can we just prime the first function and prime the second function? Okay? We're going to explore here what that would look like. Okay? So u prime, that would be the derivative of the first function. The first function is the x squared plus 3x. Okay? The derivative of that would obviously just be 2x plus 3, and then the derivative of the second function, well, that would just be a 2. Okay? And it's easy to see when we multiply this out that if we were to apply this approach, f prime of x would be 4x plus 6. But clearly, this is not equal to what we had when we avoided the product. Okay? So the question is, which one of these is correct? Well, we're more trusting in the first method, given what we've already learned in this course, that we can multiply those products out for those polynomials and take the derivative using just the power rule. So the point we're trying to get across here is that this answer, 4x plus 6, this guy's actually wrong. Okay? So this idea that we could just take the derivative of each piece separately is not correct. One simple counterexample that proves it doesn't work is sufficient to say that's not a general rule for all functions. So how do we take the derivative of a product? This is where this formula in the formula booklet comes in, known as the product rule. Okay, so they've written it with the dy dx notation. They say dy dx equals u dv dx plus v du dx. And we're going to put that in kind of words in a minute, but before we do that, we're going to write it with the prime notation. Okay? So this would be u v primed plus v u primed. So essentially the derivative of one function times the other undifferentiated function plus the other combination that you didn't do in the first part. Again, I'm going to put that in words, and I'm going to think about this rule as essentially having four pieces. So I'm going to use this 4 parenthesis skeleton on most of the problems I do. Okay? So the first parenthesis refers to this function right here, u, and what that is in words. Okay, so in words, I think of that as that's just the first function. Okay, not differentiated, just the regular first function. That's the green parenthesis right there. Okay, the blue is the dv dx. Okay, the second parenthesis, that's going to be the derivative of that second function. Okay, so we've got regular first function times derivative of second function. Our third parenthesis would be the v, and we know that that's just the second function, not differentiated, regular second function right there. And then finally, the fourth parenthesis is this du dx, okay? And that is just the derivative of that first function. Okay? So there's a nice kind of pattern to this rule. It's quite easy to use. One of the nice things is we're dealing with addition and multiplication here, so we can be a little kind of loose with the order we do these things and not end up with an incorrect result. So let's do our first example using the product rule, and we'll do this polynomial example again just to kind of give us confidence that the product rule works and obtain that same answer we had before. Okay. So we'll go nice and slow through this first one. We'll define our two functions u and v. U will be x squared plus 3x, and v will be 2x plus 1. We'll get the two derivatives ready before we try and substitute it all into the rule in the red box. These two derivatives, we've done them before. They're 2x plus 3 and 2. Now we have all the ingredients. We can set up that skeleton with our four parentheses, and it's just a case of filling in each one of these parentheses. So we can use kind of a crisscross motion with these ingredients to get them into the parentheses correctly. Okay. So the first parenthesis should go something not differentiated, so I'll do u there. And the second parenthesis should be followed by the other derivative. So that's that first red arrow going diagonally from top left to bottom right. So that would just be for 2 for us. And it's okay if these parentheses are kind of oddly sized. We're going to clean all this up in a minute anyway. The third parenthesis will be another function not differentiated. It's the other ones. We've already used the x squared plus 3x. Here we're going to use the 2x plus 1 multiplied by the other derivative, and that's the 2x plus 3. So technically this is the derivative of that function. Obviously we want it in a more usable form. So we're going to multiply it out just to confirm that we get the same standard form polynomial we had before. So this is 2x squared plus 6x plus 4x squared plus 6x plus 2x plus 3. And combining our like terms, this should give us 6x squared plus 14x plus 3. And while this does not constitute a full mathematical proof, it's pretty good evidence that we get the same result as we did earlier when we talked about multiplying that out and just applying the power rule. So we can see the same result right here using the multiplying out method as we do using the power rule. Now this example doesn't really show the advantage or the power, I guess, of the product rule. The product rule is really used for functions where you can't multiply out and you can't just apply that straightforward power rule. So when you start getting mixtures of different families of functions, so something such as x squared sine x, okay, we're asked to take both the first and the second derivative here. So clearly we need a product rule because there's multiplication in there between that x squared and that sine x, and we'll follow the same procedure again here where we make the first function u, that's our x squared. We're going to get our ingredients ready with our derivatives. And we know the derivative of x squared is 2x, and the derivative of sine x is cosine x. And then we glue all these together in our little 4 parenthesis skeleton to get our first derivative. Okay? So x squared can go in the first parenthesis. The derivative of sine x is cosine x. That can go in the second one. Sine x can go in the next one. And then 2x can go in the final one. And again, this is technically the correct derivative, but we want to clean this up and kind of make it a little more user-friendly. So we'll drop all the parentheses, and we'll move the trig functions to the front of each expression. And that's our first derivative. Not too bad, pretty straightforward, quite an easy rule to follow. Things get a little more complicated with this second derivative because we've got 2 products to do. Okay, so we've got our first product with this x squared cosine x, and then we've got our second product with this 2x sine x. Okay? And if we're feeling comfortable enough with the rule now, we can try and do this without getting all the ingredients ready beforehand. Okay? So we're going to actually need 8 parentheses here, 2 lots of 2. If we run out of room on one line, we'll just go to the next line, and we're going to try and fill these in as we go. Okay? So the first two sets of 2, okay, I'll underline them in green, okay, those guys are going to come from the derivative of x squared cosine x. The next two parentheses, two sets of 2, sorry, underlined in red, those are going to come from the derivative of 2x sine x. So starting with the green one, okay, we'll take the derivative of the first function, that's 2x, that's the derivative of x squared. We're going to leave the cosine x alone. We're then going to leave the x squared alone, and we're going to take the derivative of cosine x, which we know from the previous lesson, that's negative sine x. So the derivative of the x squared cosine x is now complete. The remaining parentheses are filled out from the second product, which is the 2x sine x. So again, we'll take the derivative of the first function, that's 2. We'll leave the second function alone, that's the sine x. We'll leave the 2x alone and take the derivative of sine x to get cosine x. Now the cleanup crew comes through and makes this a lot neater and a lot cleaner. It's 2x cosine x minus x squared sine x plus 2 sine x plus 2x cosine x. Okay? Now we have a few like terms we can combine here. It's those 2x cosine x's. So this second derivative can be computed as negative x squared sine x plus 4x cosine x plus 2 sine x. And this example should give you a real good feel for how the product rule works and the real places it's needed in the math world. Moving on to a slightly more abstract example. Okay? This is a problem where we're challenged to work with unknown functions. Okay? We're not supposed to find those functions, but we are supposed to use just the information and the data points in the question that we're given. Now, one of the big tips in IB is that they generally don't give you things you don't need. So as we go through this problem, we're going to check that we're using everything, and if we don't use something we were given in the question, that's going to be a big red flag for us that we may have done something wrong. So we're told that a function h of x is defined as the product of f of x and g of x, and we're told some information about those functions. So f of 3 is 2, g of 3 is negative 1, f primed of 3, the derivative of f at 3 is 10, and g primed of 3 is negative 2. So we essentially have 4 pieces of information, and as we go through the problem, we're going to make sure we use all 4 of those. What are we actually asked for? We're asked for the gradient of the tangent at x equals 3. So this problem will take 2 steps. Okay? First thing to do will be to find h primed of x. The second thing will be to calculate, meaning we'll use numbers, h primed of 3. So we're going to find the derivative first, and then we're going to substitute in that 3, and that will give us the gradient of the tangent, because we know the gradient of the tangent, that's the first derivative. So to find h primed of x, to do that first part, okay, we're going to apply our product rule. So that would be f of x, leave the first function alone, take the derivative of the second, the derivative of g of x, we don't know what g of x is, so we've just got to notate that as g primed of x, plus leave the second function alone, take the derivative of the first. Okay? That's f primed of x. Now, the most common mistake here is people apply the rule we started this lesson with. Okay? They think that h primed of x is just f primed of x, g primed of x. They can just prime these two functions without completing the product rule. And we know from that first example we showed with the polynomial that that doesn't work, so there's no evidence that it would work here either. Okay? We also won't use all the data points if we do that, which is another big red flag. So now that we've got our derivative, it's simply a case of substituting in that 3 into these 4 functions. So f of 3 times g primed of 3 plus g of 3 times f primed of 3. And this is where we get a nice bit of feedback on the question as to if we've done it correctly, if we have a number for each one of these 4 things. Okay, so f of 3 we were given in the question, we know that's a 2. So if we're tracking in the question, check, we've used that first piece of information. G primed of 3, we're given that's -2, so we can check the last piece of information. G of 3, we're given as -1. We'll check that one as used. And finally, F primed of 3, that was 10. We'll check that as used. So 4 pieces of information in the question. We've used all 4. That's a good sign. Now all that we need to do is a little bit of number crunching. This is -4 minus 10, giving us the slope of our tangent line is -14. And that's really all there is to the product rule. We will finish this class with a couple of IB questions if you're interested. If not, you should be good to go ahead and tackle your homework and have a good understanding of the product rule at this point. So our first IB question comes from a paper 2, but we don't need to use the calculator for many of the pieces as we have command terms such as show that and some write downs. Okay? So we begin with part A, where we're asked to show that the first derivative of e to the x times 1 minus x squared is e to the x times 1 minus 2x minus x squared. So clearly this is a product rule problem. Okay? Our two ingredients, u and v, these guys should be e to the x and 1 minus x squared. Okay? We can get their derivatives nice and easily, picking up our partial credit for using the product rule. The derivative of e to the x is just e to the x, and then the derivative of 1 minus x squared, we don't even need the parentheses around this, should be -2x. Okay? We glue all this together in our product rule to give us f primed of x. We'll get our 4 parenthesis skeleton set up here. And we take the first function, e to the x, the derivative of the second, -2x. We take the original second function, 1 minus x squared, and the derivative of the first function, which is also e to the x. There's a common factor of e to the x in here, giving us -2x plus 1 minus x squared, and a simple bit of rearranging gets us to the point where we have the answer they asked us to show, e to the x times 1 minus 2x minus x squared. Okay? 3 marks of that seems about right. We're then told that part of the graph is shown below, and the x-coordinates of the local maximum and the local minimum are r and s respectively. So we definitely want to mark that on our diagram and just make that connection that the x-coordinate of this minimum is r, and the x-coordinate of this maximum, that guy's going to be s for us. In part B, we're told to write down the equation of the horizontal asymptote. We could graph this on our calculator and confirm, but it's pretty clear this graph's got a horizontal asymptote running along the x-axis, and that horizontal asymptote is really only applying on the left side of the graph here. So as x approaches -infinity, we can see f of x is approaching 0. Okay? Horizontal asymptotes, we have this bad habit of drawing them all the way across the graph, but they really only apply on the edges describing the end behavior of those functions. Okay? So it's okay to cross a horizontal asymptote as long as you're not on the quote-unquote edges of the graph. That's a very unmathematical definition with edges, but you get the idea. It really only describes what the graph is doing as x tends to positive infinity or negative infinity. So that's basically an easy kind of free mark for us. We're now asked to write down the values of r and s. Those are the x-coordinates of the local maximum and the local minimum. The write down is a little misleading here because they're giving us 4 marks. Okay? Essentially, we need to solve the derivative equaling 0 because we know these are the local maximums and the local minimums. Okay? That gets us to this point using our answer from part A, and we know that e to the x cannot equal 0 because that's exponential growth, which means we're really trying to solve this quadratic right here, 1 minus 2x minus x squared equals 0. We can try and factor that. I don't believe it factors. We can also try the quadratic formula, but on a paper 2, we might as well utilize the tools we have, which in this case is going to be the calculator. So at this point, we'll switch over to the point where we have a calculator, and using our TI Inspire, we can go ahead and have the polynomial tools, find the roots of this polynomial for us. Okay? So it's degree 2. We want real solutions. We're just going to fill in our coefficients. Our coefficients are -1, -2, and 1. If you put that quadratic in the standard form, you can give this to polyroots, and it will spit out these two values for you. Okay? So we have x values. This -1 would be r. So we would have r equals -2.41 to 3 significant figures, and s equals 0.414. So good use of the calculator to do some quadratic solving for us right there. Finally, for 4 marks, we're told L is the normal to the curve at P. P is 0, 1, so we definitely want to mark that on our picture here. Okay? Here is P, it's the y-intercept. Okay? We have to show that the equation of L is in standard form, x plus y equals 1. Okay? So from our work in a previous class, I believe at the end of Unit 5, we know that for the equation of a normal line, we need a point and we need a perpendicular slope. Okay? Well, the point is very straightforward. We were given that. We know the point of tangency is 0, 1. The perpendicular slope will come from f primed of 0 and then the opposite reciprocal of that. Okay? So we have our derivative. It's just a case of substituting in 0 in for x. We know that anything to the power 0 should be 1. So this is essentially 1 times 1, which gives us 1. Okay? This is the slope of that tangent line. They're asking us about the normal line, so we want something perpendicular. Perpendicular to that would be a -1 slope. We can begin building our point slope form, or because we're actually given the y-intercept here, we can jump straight to slope-intercept form. We'll do that. We'll go y equals -1x plus 1. A simple rearrangement gets this to the form we want and completes this little IB problem for us for our 4, 4, 1, 3, 12 marks for us on that one. Our final question in this set of notes comes from another paper 2, and it goes as follows. We're given this function, f of x. We're told that it is e to the x sine x, and x is in radians, and we have this piece of the curve that's given to us right here. It tells us there's a point of inflection at A, so we can make that a little larger so we can kind of see it as a point on the graph. There's a local maximum at B, that's pretty well labeled, and the curve intersects the x-axis at point C. So again, most of this information is shown, we're just highlighting that inflection point a little bit. So for 1 mark, we get this command term of write down, and we're asked to find the x-coordinate of point C. Okay? The write down is kind of the clue and the giveaway here. We're going to let the calculator do this for us. So we type this function into our calculator, and we're able to reproduce a very similar graph, making sure we're in radian mode and getting that window set up 0 to 5 on the x-axis and about -6.67 to 10 on the y-axis. We can find this value C, that's just the x-intercept, by simply going Menu, Analyze Graph, and it's called a 0. Okay? So this C value comes out to be 3.14, which is likely pi. We can just write down the decimal value, though, to get our 1 mark. X equals 3.14 right there. Second part of the question, we are asked to find f primed of x. So this is the derivative of f of x. Okay? This is something we have to do manually. The calculator is not going to help us. So we're going to apply our product rule here. We'll get our u and our v set up down the bottom. U will be e to the x, v will be sine x. We'll take our derivatives. So derivative of e to the x stays e to the x. Derivative of sine x we know is cosine x. Okay. It was sine x, not cosine x. And then we can glue our derivatives together with our 4 parentheses structure that we've been using throughout this set of notes. So first function e to the x, derivative of second cosine x. Second function sine x, derivative of first e to the x. And we can clean this up a little bit by factoring out an e to the x and then throwing the cosine x plus sine x in a parenthesis there. And that's probably about as clean as we're going to get that derivative right there. We're asked to write down the value of the derivative at point B. We know point B is the local maximum. We know the tangent line at a maximum is horizontal, meaning it has a slope of 0. So the write down command term again gives us a little clue. We should know this value, f prime of b, that should equal 0, and that'll get us our 1 mark with that write down command term. Moving on to part C, we're asked to show the second derivative is 2e to the x cosine x. So that's the derivative of the derivative. Again, that's another product rule. In this second derivative, the first function is e to the x. The second function is sine x plus cosine x, or cosine x plus sine x. We'll get all of our ingredients ready, our u prime and our v prime. This will be negative sine x plus cosine x for our derivative of cosine x plus sine x. We'll glue all this together in our parentheses. Throw all the ingredients into the recipe. E to the x times minus sine x plus cosine x. We'll squeeze that in there. And then that's times cosine x plus sine x times e to the x, multiplying out this algebra. This would be negative e to the x sine x plus e to the x cosine x plus e to the x cosine x plus e to the x sine x. Okay. We've got the answer given, so that's a clue that these e to the x sine x's should cancel, which using our algebra they do. And we get our second derivative here of 2e to the x cosine x as they requested. Okay. That finishes out that little show that problem. And the last things we need to do, write down the value of f double primed at the point of inflection. Again, write down as a clue. We know the second derivative at a point of inflection has a value of 0, so we can get that free easy mark. That's a 0 as well. Hence, calculate the coordinates of A. We're going to solve an equation for that. Let me put another page in here real quick. Put in. We need to solve this second derivative equal to 0 equation. We're going to use our calculator for that part. So in D part 2, we want e to the x cosine x equal to 0. And we know that x, using our graph, is somewhere kind of between about 0 and 5. That's how we set up our x-axis. So we'll give our numerical solver a little range to work with, e to the x cosine x there, 0 to 5. And we'll let our calculator go to work on that. So we come back to our calculator here, and we're going to insert a calculator page to solve this equation. We are going to go to our numerical solver, which is menu 3.1, and we are solving e to the x, no, 2e to the x, 2e to the x times, and then we want our trig function. Our trig function here is cosine x. We want that equal to 0. Our variable we're solving for is x. And our little range, or our domain that we want to solve on, somewhere between 0 and 5. Okay? And it spits this out nicely for us as 1.57 to 3 significant figures. If that number looks familiar to you, that is actually pi over 2. So that completes our work on the product rule. Again, if you found this video useful and the couple of IB questions we've answered here, please go ahead and like the video, subscribe to the channel, and leave any comments you like down below.